independent random variables and independent fields. Recall we said two random variables are independent only if you compute the for any two Borel sets saying that x is in B1 and y is in B2 are independent. What do you mean by that? So we know two events are independent. If you say that, okay, the probability of intersection P is probability of K times probability of K, something standard. So now, using this, I can define independence of two random variables, and the answer is yes. What you need to just do is that take any two Borel sets and consider the collection of those omegas from omegas for which x of omega is in B1. So that's a set actually. Okay? And similarly, consider the collection of those omegas for which the y of omega is in B2. So that's another set. And these B1 and B2 are two arbitrary Borel sets. Then we say that two random variables are independent if and only if, actually if you see, this is nothing, this is just inverse image of the Borel set B1. And this is the inverse image of the Borel set B2. Okay? In other words, two random variables are independent if for any two Borel sets their inverse images, okay, are independent from each other. Okay. So it's like breaking down definition of the independent random variable to the independent set circle. And if this is true for all B1 and B2, you can say that two random variables are independent. So this is something that we also discussed. Then we also define what we mean by a sigma field generated by a random variable x. In order to define it, consider the collection of all inverse images of the Borel set under X. Okay. So that's a collection of inverse images, collection of all inverse images of the Borel sets. So that's a collection. Then by sigma field generated by X, I mean the sigma field generated by this collection. Okay. So what do I mean by that? We'll do several examples of it. With conditional expectation, you'll see several examples of it. But essentially, when I say that sigma field generated by a random variable, I mean that sigma field generated by the inverse images. In other words, every element in this sigma field is either such kind of a set or the union of such kind of a set. Okay? Then I can also define what do I mean by two sigma fields to be independent actually. So imagine I have a sigma field F. So let G1 and G2 are two subcollections under the sub-sigma fields of a sigma field F. Then G1 and G2 are independent. In other words, these two sigma fields, sub-sigma fields are independent if and only if, what happens? For any two events from these sets, those two events are independent actually. So in other words, take an event from here, take an event from here, then both must be independent of each other actually. If and only if for all, say A from G1 and B from G2, A and B are independent. So you see, everything, again comes down to the same basically definition of independent sets. We say that, random variables are independent, if their inverse images for Borel sets are independent, the sigma fields are independent. If you arbitrarily pick any two, measurable sets from the sigma fields, then they are independent. Okay. One of the example, a trivial example could be that let's take two independent sets. So let's take two independent events. They are subsets of a matrix. Then consider these two sigma fields. Empty set A complement and omega. And consider this sigma field as well. Empty set B complement and omega. Okay. These are also independent. Is it making sense? Indeed, if I take an empty set from here, the identity is satisfied. If this is the underlying assumption that you have two independent sets B, then A and B are independent. A and B complement are independent. Okay, we can easily prove this proposition. A complement and B are independent. Okay. So in other words, if happening of two events is independent of each other, then their not happening is also independent of each other actually. So that's one happens, another doesn't happen, and one doesn't happen, another happens. They are also independent actually. Okay. And thus you can prove a proposition. I gave you this proposition last time to prove actually, so you must prove that as well. So these are, this would be one of the easiest example of, maybe you can also verify that why this is given in the form of an exercise 3.29 in the book. Okay. I'd like to prove a proposition. Let's prove a simple proposition. So these are important facts that you must always keep in your consideration. precise formulation of proposition. So it says that if x and y are independent random variables, if x and y are independent random variables, okay, and u comma v are measurable random variables with respect to sigma field generated by x and sigma field generated by y respectively. Okay. Then u comma v are also independent. Okay. By the way, one of proposition that you can prove easily, and it's just evident from definition, is that if you have two random variables which are independent from each other, then the sigma fields generated by that random variable would also be independent from each other. Why this would be the case? Because think about it. For random variables, you want inverse images to be independent for every Borel set. And from the same Borel set, you are constructing the sigma field. So if these events are independent for every Borel set, obviously, and sigma fields are generated by such kind of events, so the sigma fields also must be independent. In other words, if you have two independent random variables, they must generate an independent sigma fields. And in fact, you can prove this if and only if a statement that if two sigma fields generated by the random variable are independent, then the random variables must be independent too, actually. So what does this proposition is telling you? It's telling you that imagine you have two independent random variables, and obviously these two independent random variables will generate two independent sigma fields. And now take any two measurable random variables with respect to these two sigma fields, then u and v are also independent. Okay? Yes, sir. By the way, what do we mean by u and v being measurable with respect to the sigma field generated by x? What is the meaning of u being measurable with respect to the sigma field generated by x? In other words, what is the meaning of u being measurable with respect to one sigma field?
Contains that
X inverse of
So you take the inverse images of the Borel sets. They must be in the
sigma field.
okay. So as this is one of the things. So what you have to just do is basically this, that so in order to show that u and v are independent, so after this reviewing this definition, what you have to just show, you have to take two arbitrary Borel sets. So let B1 and B2 be two Borel sets, okay, and consider the sets, this u is in B1 and v is in B2. Okay. Basically, this would be the notation that we are going to use for what? For the inverse image. I'm not going to write u inverse of B1. Basically, this means that it's a collection of omegas for which the u of omega is in B1. And it's a collection of omegas for which the v of omega is in what we call B2. Okay? What should be the next step? So as u and v are, measurable with respect to the sigma field, sigma x and y. So as u comma v are measurable with respect to what? Sigma field generated by x and sigma field generated by y respectively. So what does this mean? This means that these two guys must belong to respective degrees. So u in V1 belongs to sigma field generated by x, and V belongs to V2 must belongs to the sigma field generated by y. Okay? Respectively. And now, what does this mean? Now since x and y are independent, so these two must also be independent sigma fields actually, as I said previously. Okay? So maybe one of the exercise that you can do is that x comma y are independent if and only if sigma x and sigma field generated by y are independent. Okay? So let's do this exercise. This just follows the from definition. You don't have to do anything. Now since these two sigma fields are independent, what does this mean? This means that these two events u belongs to V1 and V is in V2 are independent. Okay. And this completes the proof. That's what we needed to prove actually. You take two arbitrary Borel sets and show that these sets are independent. So why they are independent? Because they belong to the independent sigma fields. That's it. Okay. One of the interesting corollary of this result is going to be this. Corollary of this result is that if x and y are independent random variables and g and h are maps from R to R that are Borel measurable, then g of x and h of y are also independent. Is it making sense? Okay. This is one of the very, very interesting results. Why this is so let's just see that why this follows from this result actually. Why this follows from this result. And then we'll talk about that what does this result mean actually. Now think about it. So if x and y are two independent random variables, okay, then they'll generate independent sigma fields. That's one of And if you have two Borel measurable sets, okay, two Borel measurable maps, then we also know that if you compose a Borel measurable map with a random variable, that's a random variable as well. Okay, so that's a measurable random variable as well. And similarly, this is also a measurable random variable as well. Okay. The only thing that you have to just verify is that why this random variable is measurable with respect to the sigma field generated by x, and why this random variable is measurable with respect to the sigma field generated by y actually. And this must be easy, think about it. So just take the, just take the G composition X, its inverse image over B actually. What are you going to get? So you're going to get X inverse composition G inverse of B. Now since this is measurable, okay, what's going to happen? It's a Borel set. So Borel map is what? It's mapping the Borel sets onto the Borel sets. Okay, so in other words, if the B is a Borel set, then this, since being the Borel set, belongs to the Borel sigma-algebra because G is a Borel measurable map. That's what the Borel measurability means. So that's a Borel measurable map. And since this is Borel, then X inverse of the Borel set overall must belong to the sigma field generated by X by definition. So in other words, this guy, belongs to X for all. What do you call? Yes. Yeah. Okay. So X is a what? So X is independent random variable, but X is independent of Y, but X is going to generate a sigma field. So from every random variable you can generate a sigma field. Okay? And obviously the X is measurable with respect to that generated sigma field itself. In it. Okay? So every random variable is measurable with respect to its generated sigma field. Okay? And now, and this also follows from definition actually. So what does this follows from here is that the X inverse of the Borel set belongs to the sigma field, etc. And similarly you can do this for Y. Okay? And hence what this shows is that these two variables. So in other words, if you take a random variable and you compose it with the Borel map, so that map is also going to be the compositions are also going to be independent. So see, when we were starting this chapter, we said that what if I would like to prove that x squared plus 2x and plus, for example, sin x and say sin square x plus what do you call e to the x e to the y. So if you know that x and y are two independent map, then can these two maps be also independent? I mean, if you try to do it from your classical probability theory, that's a very trouble-making thing. But now think about it. I mean, if you see it from this proposition, so if you know that x and y are two independent random variables, you compose it with any, say, continuous map. Borel map not necessarily to be continuous, it's more than continuous actually. Continuous are Borel, for sure, but it's not necessary that every continuous map must be called Borel. That this theory allows you to say that these two are independent. You don't need to get into your messy calculations actually. Is it making sense? So it's the such kind of results that are making your life way easier. Okay. So you can take a complicated kind of an expression, just make sure that expression is moral. Okay, usually we love to approximate things through continuous things. So independence will automatically come out. Anyway, so that's a power of the result. That if you have if you have two independent random variables, then you compose them with any continuous map. Okay, then they will be independent too. Okay. By the way, you can generalize all this analysis for any finite n actually. Okay, you can do it for infinite dimension, but yes, you can define things at least for finite very easily. In other words, if you have n random variables, then when they will be independent. So we know that if you have been given n events, what is their how to prove their independence. So what you have to essentially do is that just take arbitrary combination of intersections actually, okay, from n, okay, and verify this product identity, the definition. In that, if I have a1, so how I'm going to say that these events, n events, are independent of each other?
Intersection.
So just take the all possible intersections and compute the probabilities of those. All possible intersections. So in other words, two intersections, intersection of 3 sets, 4 sets, all possible 4 sets, 5 sets, 1 and so forth. So it will be, so in other words, take any, okay, AI1 intersection, AI2 intersection, for example, AIK, where all of these IKs, okay, AIJs are from 1 to, for example, K. Okay, let's not use K, but let's use J. Some J or maybe L actually, something like that. And the probability of this is equal to the product of the probabilities. I equal to 1 to L and for example, M equal to 1 to M, KIM, product of the probability. So this is the way to say that these events are independent. Is it making sense? So if you know this, then I can easily define what do I mean by n random variables being independent. So it means that take n Borel sets, consider their inverse images, and if they are independent from each other in this sense actually. Okay? So you're going to say that these are Borel sets. So in other words, the results that we have proved for two random variables, we can easily prove them for n random variables actually. Okay? So slight generalization is always possible. So read it out. This is stuff. It's not a big deal. I'd say must do these exercises. These are the small exercises basically. So 3.29, say for example for 3.33, I'll tell you more later. The next is, I would like to define is basically a property. So I'm not proving that property, but I highly encourage you to look into that proof. It's a simple proof in the sense that you want to prove something for, say for example, random variables.